This is the summary created from the video. Lecture 58 Case Study I Spatial Cloud Computing. In this video, we explore the concept of PHIL experimentation, which connects real hardware devices like wind and solar generators to simulated networks in a closed-loop setup. Power is exchanged between the real-time digital simulator and the hardware through power amplifiers with DA converters scaling down simulator signals for compatibility with the hardware interface. The GTAI and GTAO cards play a crucial role in the PHIL setup. The GTAI analog-to-digital converter card receives AC signals from a function generator, representing input from the power hardware device, while the GTAO digital-to-analog converter card sends scaled signals from the simulator to the hardware via the power amplifier. In the demonstrated DFIG-WTG setup, a 2.2 kW doubly-fed induction generator is connected to a simulated distribution network through a power amplifier. The grid voltage is scaled and applied to the DFIG system, initially charging the DC link. The phase-locked loop synchronizes the DFIG with the grid, and the rotor side converter controls power extraction from wind. To analyze symmetrical faults, the DFIG wind system is exposed to a 50% stator voltage dip in each phase for 5 cycles. This disturbance induces high rotor voltage, affecting the converter currents and DC link voltage. Phase current and voltage variations highlight the symmetrical nature of the fault, with observed active and reactive power fluctuations. In contrast, asymmetrical faults, such as a line-to-line fault causing a 50% voltage dip in phases B and C, lead to greater disturbances in the converter currents and significant DC link voltage issues due to converter limits in handling in rush. Rotor currents, asymmetrical voltages and negative sequence components cause larger active and reactive power variations. Comparative analysis reveals a clear distinction between symmetrical and asymmetrical faults in terms of flux speed, DC link voltage variations, and converter current disturbances. Asymmetrical faults induce higher rotor voltages, causing increased flux variation during transients, leading to larger speed changes and increased current perturbations in the converters. The PHIL setup enables comprehensive analysis of DFIG wind turbine behavior under various grid disturbances, including symmetrical and asymmetrical faults. The results demonstrate that asymmetrical faults greatly influence the transient response. With twice the flux variation, drastic speed changes, increased converter current disturbances, and significant fluctuations in active and reactive power injection. In conclusion, the lecture covered PHIL experimentation for symmetric and asymmetric fault analysis of grid-connected DFIG wind turbines in detail, aiming to encourage further laboratory experiments and research in this field. The presented material is expected to motivate the audience to explore this topic further. Please stay tuned for more summary videos.